And share the screen. Okay, so can everyone see the slides?
Yes.
Okay.
Sure
Let me get
can.
my little remote here. Okay. So welcome everyone. This is the first of what intend to be many sessions on electromagnetic interference test methods, mainly per GEVS, the General Environmental Verification Spec, the Goddard specific document, and Mill Standard 461, primarily the latest version G. We'll talk about that here coming up. So this is an introduction and overview session with sessions on detailed, the individual detailed test methods to follow over the next many weeks. You know, this is going to be interesting with going to be a noise out in the hallway, but there we are. Well, we need to keep the doors open so that I have a Wi-Fi signal.
Yeah.
So
Okay.
look, we're just going to have to live with it.
Okay.
So, all right, we're going to get on with it. And fasten seat belts, trays in full upright and lock position, and let's get going. And no, that's not working. Okay. Oh, I'm not in the right window. Hold on. The technology, it's great. There we go. All right. So just some general thoughts here. A general approach, mine anyway, is learning about electromagnetics is not about memorizing facts, figures, and so on. It's not about black magic, pointy wizard hats, magic wands, and so on, even though those may, I was going to say those make us look cool, but we're engineers. We gave up on cool decades ago. But what it is about is learning a whole way of thinking about things and solving problems, and learning the language to communicate effectively with other EMC professionals. And it is a language. Every discipline is something akin to a language, right? So actually I didn't put it on the chart. Maybe I will for future editions. But one of the examples I always like to give is BOWIE, Maryland. When you first moved here, because most of us are transplants, what did you call the name of that town?
Bowie.
Bowie, thank you. Don't be bashful, I did too. You called it Bowie, Maryland, and how many nanoseconds did it take people to correct you? Not many, right? They yell very loudly, it's Bowie. It's not Bowie. You don't get to come in and unilaterally say it's now Bowie. No, it's Bowie. So when you are learning any kind of a discipline, there is a language, there is a nomenclature, and it's on you to learn it so that you can effectively communicate with other people in the discipline. We get that all the time. Oh, you EMC guys are so picky about your nomenclature. And if it's a thermal engineer, I'll say, okay, let me start getting sloppy with your nomenclature, and we'll see how fast you correct me, right? So just make sure, you know, it's all about EMC literacy, just being and to be able to effectively communicate. And this is probably the most important bit in the context here, providing a framework on which to build your ongoing knowledge and experience base. There's not that much of a secret that I am planning my retirement. Don't have a specific departure date yet. I've got a target that I'm not going to say out loud. But, you know, I really want the center to continue to be able to do effective EMC work, you know, once I go ride my bike off into the sunset. You know, it's not in anybody's interest for me to take everything I know with me. That's why I'm doing this. So moving right along. And and it's also about the laws of physics. So some terminology. Electromagnetic interference is the phenomenon in which one component or subsystem interferes with the proper operation of another subsystem due to the propagation of electromagnetic energy. Don't worry, I'm not going to read every single chart word for word, but sometimes I will, like this. So electromagnetic compatibility is the discipline of ensuring that electronic components and subsystems function together, play nicely together in the resulting environment. So the way to think about this is we control EMI in order to achieve EMC. This is one of those nomenclature things. EMI and EMC tend to get kind of lazily interchanged, and they are distinct. They're obviously very related, but they are distinct. And it's just important to keep track of that difference. So with the EMI, you have clearly my cultural references need to get updated, but here we are. But you'll have a culprit, or in some circles it's called an aggressor, but it's the same thing, which is a component or subsystem that is an emitter of electromagnetic energy. You will have a victim. Does anybody know how to get rid of this? There we go. It probably will pop up again, but there we are. All right, you have a victim that is a component which is a component or subsystem that is susceptible to electromagnetic energy. I like to say that it conceptually at this level, my job is pretty straightforward. The universe is divided into two things: noise-making things and things that are sensitive to noise-making things. So, and any given device can be both depending on context. And then you need a coupling mechanism, which is the process by which the energy emitted by a culprit causes interference in a victim. So to have an EMI problem, you need all three. And to fix it, you need to address at least one of them. Okay? It's pretty straightforward, but that's really the crux of everything we do. You need a culprit, a victim, and a coupling mechanism. So EMI testing is best performed at component or unit level to address these problems before integrating onto the platform. Emissions tests are designed to assess emissions from culprits or aggressors, as the name suggests. And susceptibility tests are just designed to assess susceptibility of victims. Right? You want to beat down the risk of emissions and susceptibility before you put everything on the platform and just assess compatibility. That is the ultimate check, but you want to do these tests beforehand to minimize the risk of any interference problems once you integrate onto the platform. And your primary coupling mechanisms are conducted, radiated, and crosstalk. Crosstalk is kind of in a middle ground between them, but those are our three basic coupling mechanisms. So typical culprits and victims on spacecraft. For culprits are radio transmitters, switching power converters. That's a big one, really, and that's actually our sample EUT here that we'll use for further sessions. And we're not really going to do anything with it today, other than show and tell. But switching power converters is a big one. Motors, cryocoolers, high-speed digital electronics. The running theme here is current, either high current devices or high speed switching. Right, high speed digital electronics may not be carrying a lot of absolute current, but it's that DIDT. It's a rapidly changing current that can be a significant emitter. And victims tend to be radio receivers, detectors, sensors, and low-level analog electronics. And obviously, this is not an exhaustive list. It's just, something to get you thinking about it. So why are standardized test methods important? Well, for emissions test methods, a proper measurement technique will ensure accurate and repeatable results. And that's very desirable for fix or no fix decisions, right? You want to make sure your results are reliable so that if you have to fix something, you know why, like that, that it's not a measurement error, right? For susceptibility test methods, proper test techniques ensure accurate, repeatable, and controlled signal injection levels. That minimizes the risk to the hardware, because any susceptibility test carries some inherent risk, right? You want to make sure you're applying a controlled level that's not going to damage or stress the hardware. That's desirable for obvious reasons. So the running theme here is accuracy and repeatability. And one that I will stress, it's maybe a little less technical, but I think this is extremely important. Credibility when you share your procedures and test reports with external organizations. And well, external could even mean within your own, it could basically be internal organizations. At some point, you got to share test results with, say, project management or systems engineers, saying, hey, we failed conducting emissions miserably on this box. We need to delay integrating it onto the spacecraft and fix this, because this could be a significant problem. So having accurate and repeatable test methods really enhances, it gives you that credibility when you go to management or whomever and say, we got a problem, or that we don't have a problem. So, but this credibility is extremely important, because you will be sharing test procedures and reports with other people, and they need to have the confidence that you knew what you were doing and didn't just slap something together. Okay. So we're gonna play a little game here. Name that painter. And those of you who've already played this game, keep mum. But and I'll give you the answer at the end. So tell me who the painter is, and also what was the painter's age at the time of this work. So keep that in mind, and then and you'll understand why we're playing this game in the context of it when we get to the end. There is always a reason. May not be obvious at the outset, but when I do this kind of crap, there's always a reason, there's always a point, and I'll tell you when we're done. Okay. So those of you who know me already know that. But anyway, so GEVS and EMC. Baseline EMI requirements and test methods for Goddard programs are defined in this document we call GEVS. The general, and sometimes the G is misquoted as Goddard. It's not, it's general. General Environmental Verification Standard, even though it is a Goddard document. So the full title is General Environmental Verification Standard for GSFC flight programs and projects. And it's GSFC Standard 7000, and it's up to Rev B right now. Released in April 2021. It is called a mandatory Goddard standard, and it's available at the link shown there. And that is the place to go for Goddard. I believe that's Goddard's that's NASA standards, and I think it's a link for center standards, so you go to Goddard. This is primarily based on Mil Standard 461G. So there's a definite interconnected relationship between these documents. I'll get into that here presently. Mil Standard 461H update is in the works. I know a few people who are on the committee handling that. Some of them might even be on the line here. I've submitted a comment, rather extensive comment to it that I believe might get incorporated. It has to do with the CS 101 test method. We'll get to that when we get to that session. But anyway, but GEVS also references all these documents here, a couple of previous versions of Mil Standard 461, also Mil Standard 462, 464, the space shuttle spec that we call SLE triple ball 2, and then this AIAA spec on the bottom there, S121, the 2000. I thought I'd updated that. I believe we updated that in 2017. That the 2009 means the 2009 version. So I need to update that, because I was on the committee that updated that document, and it was about 2017. So anyway, one of the comments or questions comes up that, well, are you guys using Mil Standard 461G or 461C? Because you use stuff from both. Well, and yes, we do. And we'll talk about that here mainly in some upcoming sessions, but I'll talk about the Mil. I have a brief history of the Mil Standard here in just a moment. But GEVS section 2.5, that's the EMC section, and it is organized as follows, where 251 is the general requirements. That's basically what we're going to be talking about for the rest of this session. Includes test facility and procedure requirements, and section 252 are the detailed requirements. That's the for anybody already familiar with EMI testing, that's your CE 101, CS 101, those specific tests. That's what's in the detailed requirements. Where the general requirements are the things that we're going to talk about today, like the general layout of the test chamber and things like that. And then 253 is the application guide, which includes a discussion and rationale of the general and detailed requirements, and it's modeled after the application guide in the appendix of Mil Standard 461 by design. Right, there's a really excellent application guide in the Mil Standard that actually goes into explaining what are you actually trying to do, the engineering basis of the test. So GEVS, it's no mystery, or shouldn't be any mystery, that I spearheaded the effort to rewrite the last two the EMC section of the last two updates of GEVS. And so by design, we leveraged Mill Standard 461 as much as possible. Rev A, it was up to Mill Standard 461F at the time. But anyway, tailoring additions or noted as needed. So it's basically do such and such, per Mill Standard 461, say CS 101 test method, but then with these bits of tailoring. And so when you use GEVS, Mill Standard 461G should be kept handy as a companion document. So a counterexample is this SLE triple ball 2, the shuttle EMI spec, from which I borrowed some concepts and some ideas. That is an essentially rewritten version of Mill Standard 461E, just because of the time when it was written around, I should know this, it was early 2000s. Something like that, 2001. Mill Standard 461E was the most current version at the time. So they took people I know who were actually I know were on the committee who wrote that version of the Mill Standard. I'm sure they were able to just get a Word version of the document and make edits to it. So it's a standalone document with the tailoring incorporated. So it's two different approaches. You can either just have your own standalone document, or in the case of GEVS, I decided to just leverage the Mill Standard because we were leveraging quite a bit from it. And had I doing it the second way, it's much more time consuming. So I just made a judgment call. No, we're just going to leverage Mill Standard 461 as much as we can. So all right, here's our brief history. Mill Standard 461 and 462. It all started, and I just love to say this because it started in the Summer of Love in July of 1967. A Mill Standard in the Summer of Love. I totally know what I'm doing there, so I'm hoping people understand the irony. But anyway, so 461 at the beginning was all about requirements. And Mill Standard 462 was all about test methods. That's a very important distinction, where 461 would tell you, well, you need to meet this limit. 462 would tell you, well, here's how you do it. Okay, and so you needed both documents. And then 462 was updated, not really updated, not revised, but Notice 2 went out in May of 1970. That's really the version that we have used or had used until some of the more recent versions. But that Notice 2 May of 1970 was one that we leveraged for, and we still do for some test methods. 461A came out in about a year later in August of 68. Then 461B in 1980. Then 461C, which was a key one that we stayed on for quite a number of years, in 1987. And then in 1993, was a more significant shift where both documents were updated to Rev D, and they updated the requirements and the test methods. And this is when we went to that shift that seems to throw a lot of people, when we went from CE01, CS01 to CE101 and CS1 and CS101 and so forth. We get into the individual test methods. I'll talk about what those differences are. In most cases, it's not that significant. Not that there's zero difference, but like CE101 and CE01 and CE101, not that significant. They're basically the same test. So, but that nomenclature, I think, seemed to really throw people off who were used to the old nomenclature. And I think that's just my running theory, that's one reason Goddard just clung to 461C for so long, because that nomenclature scared people. Again, it's just my theory, but anyway, and a general test as you fly philosophy. And this is where they added that application guide to provide rationale and discussion of each requirement. So going to the latest version of a document, it gives you things to actually help you do your job. So I've never really understood this. Well, we're just going to stay with 461C and avoid all of the improvements that were made in the more recent version. So then in 1999, when they went to E, there was another somewhat seismic shift. That's when they pulled the test methods into 461, and 462D Notice 4 canceled Mill Standard 462. It basically canceled it as a document. You can still go get the older versions of the document, because I still use Mill Standard 462 Basic and Notice 2. You can still find those documents and use them. It's just they didn't update it, and it's it's just no longer being maintained. So they incorporated the test method. So now the limits and the test methods are all in the same document. And I personally think that was a change for the better, because now it's all in one document. It's all right there. Here's the limit, or at least the suggested limit, and here's how you do it. And so then in F was released in 2007. I remember that because that's that's after I started paying attention to these things, paying attention to Mill Standard 461 and EMI testing in general. And that was a less of a seismic shift. That was just, minor evolutionary updates. Then G was released in 2015. I definitely remember that. And so you are here for now. Again, minor evolutionary updates, not a real significant seismic shift. And then 461H updates are in progress. I haven't heard anything real recently on that, but I know some of the people who are involved in that, but I haven't communicated with them recently. But stay tuned. I don't expect. I expect that to be kind of more what I've heard. I've actually seen some presentations on it. I did start recording, didn't I? I'm sorry.
Yes.
Okay, thank you. Let me just make sure. That is true. Yeah, all right. Sorry, it just suddenly occurred to me I might not have started recording, but okay, I think I did. One of the fringe benefits of being 58. Just who snorted? Was that? Never mind. Okay. That I was going to say, was that Stop Whining Junior kind of snort, but so yeah, there we go. Anyway, I believe that 461H is the presentations that I've seen. I think it's more of the minor evolutionary updates as opposed to any kind of real seismic shift. But stay tuned. So system level testing. We had some previous documents here that were our references, and you can see, they're getting up in years too. So they have been superseded by Mill Standard 464. Several updates there. The latest one was released in 2020, and that's really the one that we should be using. I have some words, some thoughts I'll be sharing about using the latest version of a document here. But I'll sneak preview here is use the latest bloody version of a document, right? They updated it for a reason, and you at least owe it to yourself to know what's in there, right? Just insisting on using some previous version of a document, or that we're on contract for that, or whatever. Just my personal opinion, not necessarily NASA's or Goddard's opinion, but I just don't understand that. If you're using a standard and it was updated, you at the very least owe it to yourself to know why they updated it. So anyway, we'll talk a little more about that. Okay, ISS requirements or documents. That really should just say documents. but here's a list of ISS documents that apply to EMI testing, and the real core ones are highlighted in the middle there. 302, 37, and 38 are the equivalent of Mill Standard 461 and 462, and they use the common nomenclature. If you're familiar with those Mill Standard documents, they look very similar. The test methods are very similar, but kind of like the space shuttle spec, they wrote their own standalone documents, right? So everything is self-contained in those. And uses the same Mill Standard nomenclature, CEO1, CSO1, and so forth. Now, these these are requirements documents. If you are flying on the ISS, thou shalt use these. You can, certainly, use some ideas or or things from the mill standard that you see fit. But if you're flying on the ISS, these are the documents that you must use. So, and there's a link to where you can find them. The last time I got on there, I think you have to set up an account. You can't just get on that website and download them like a library. You have to set up an account, and being the ISS, things are a little bit more secure than maybe your average not NASA document site. So you have to set up an account, and it may take some time to get it approved. And because I think they, when I set it up, it's like, do you have some genuine need to see these documents, kind of thing. And if you don't, they might not grant you the account. So, but there it is. You can at least try it. So the mill standard documents are available on this is a public website, actually, this everyspec.com. So you should be able to grab those. And I have pretty much all the documents that I've talked about on the Teams files site. So if you're not able to access that, I think basically everybody in the EMC working group should be able to access that. If not, email me and I'll add you to the list. It takes a couple seconds. It's very easy to do. I'm happy to do that. So, okay, tailoring of requirements. This is right up front in the mill standard, section 122. I'll just read the highlighted blue sentence here. But when analyses reveal that the requirements in this standard are not appropriate for that procurement, the requirements may be tailored and incorporated into the request for proposal, specification, contract, order, and so forth prior to the start of the test program. So tailoring is welcome and encouraged, but be aware of what that means. That is not meant to be interpreted as, we don't like these requirements, we don't feel like meeting them, so we're going to meet these easier ones. That's not what that means. It means provide some engineering basis to say this requirement is way more stringent than anything we need. This is a more suitable requirement that still establishes that our device will be compatible with the system and so forth. Or it can happen the other way. I've seen it happen the other way, where the default limit isn't sufficient. You could meet that limit and still have a problem. So you want to bump the limit up to something a little more stringent, because that's what, your platform may require. But all that, it means do engineering diligence to make sure that you are testing your equipment, appropriately for your platform. It's basically my mantra: know thy platform. I think I was remiss. I didn't actually include it on this slide. But know thy platform is coming up on upcoming slides. Maybe this next one, actually. So most of these documents that I've mentioned, GEVS, the mill standard documents, the shuttle spec, and the AIAA spec, these are not requirements documents in and of themselves. They provide a menu of options, not the meal. Right? If you tell me you're testing per GEVS or even per mill standard 461, it's basically like if I'm your server at your table, you just hand me the menu and say, this is what I'll have, please. Maybe that is what you want. You're probably going to be rather sick in an hour or so, but that's a misunderstanding the point of these documents. They provide a menu of options, not the meal. So you get to choose the options that make the most sense for your project and define them in your project requirements documents. You may not feel like having a slice of pizza tonight. You want pasta instead. Okay. You get to make those choices. It's, you don't have to take everything on the menu. So think of it as get to instead of have to. All right. Now, an exception to this, those ISS documents are indeed requirements documents. Thou shalt do these things if you want to fly on ISS. Now, it's been a little while since I've looked at these documents and have tested an ISS piece of equipment flying on ISS. There may well still be options in there, for this type of payload, do this, for this type of payload, do that. So you still, have to You still, is that the case?
It's based on which
Okay.
module you're connected to. Is it an Eastern module, Jackson module, Russian module,
Right.
Massive
Right.
module? They all have different requirements.
Addendum.
Yeah. But I think within that, if you're in a specific module, it's thou shalt do these things.
Yeah.
So, but so it's just a little bit different from the mill standard or GEVS. With ISS, like once it's defined what module you're in, it's pretty cut and dry. These are your requirements. You must test to these. So, so as a provider of electronic hardware for a spaceflight mission, you are responsible for knowing all of your requirements, EMI included, how they will be tested. And so I have a mechanical analogy, intentionally absurd to make a point, that would you show up for a vibe test with only duct tape to mount your box to the table, then ask for a waiver when your box flies across the room? This is, of course, a rhetorical question, but people do that, the equivalent of that all the time with EMI. Okay, not with EMI, it's not duct tape, it's copper tape. But, you know, but with great power comes great responsibility. So Uncle Ben Parker from Spider-Man. I mean, you're building space flight hardware. So you have the responsibility to know what that means, to know what your requirements are, how to design for it, and how to test them, at least at some level. And I'll give this commercial again at the end, but I'll do it now. For whatever NASA center you're at, or wherever you're working, go pay a visit to your EMI lab guys. You know,
Hey, John,
yes.
how would you relate this to the mechanical analogy to the environment? Like, you're not going to put a 2-ton object on something that can only, do 100 pounds. Whereas, they expect us to test sometimes in an environment that's noisy. So, you know what I mean?
Well, so and didn't recognize your voice at first, but hi, Mike.
Hi.
So I'm
see
not
what I'm
entirely
saying?
sure what your question is.
Well, if you go into a chamber and it's not sealed properly, or the door's left open, because they want to have some cables coming through or something that didn't quite meet, and then all of a sudden you've got noise in the environment.
Well, we're gonna get
I
to
guess you
that.
don't run into that very often.
Well, we'll get to that. That's actually some of the specific test setup things we're gonna get to.
Okay.
Yep.
Oh shit.
Yeah.
Thanks.
Yep. But anyway, I think as long as I've been on this job, I think we've pretty much broken down that barrier between box designers and the EMI lab. I mean, it warms my heart no end. Okay, I know I'm a sarcastic bastard, and and so that I don't mean that to sound like sarcasm, because it probably did, but I sincerely mean it. That it warms my heart when project people come to us, come to me, come to the EMI lab like 6 months in advance. Hey, we're going to be testing something 6 months from now. How can we prepare for it? And
We'd love to hear that.
it honestly almost makes me cry, because that wasn't true when I first took this job, whenever that was, 12, 14, an eternity ago. About 12. What's that? What's that? Well,
Put this turntable, table on that turntable in a month.
Yeah.
Something about like they're doing at the mag. So.
yeah.
Yes.
Well, anyway, but go talk to the guys in your EMI lab. You know, we love it when that happens. Even to just say, I don't have anything immediate need, but we're probably going to do some EMI testing a year from now. I'd like to at least start understanding what that means. We'd love to hear that, and we're happy to address your questions. And those are the conversations we love to hear, much more than we're coming in tomorrow and have no clue what we're doing. But those are less desirable. So moving right along here. So, all right, getting a little more into EMI concerns or engineering concerns for EMI testing. So one of the main ones is compatibility with the power subsystem. Then you have compatibility with the radio frequency, or henceforth I will say RF communication subsystem. And then compatibility between subsystems, crosstalk. So we'll talk a bit about each one here. So compatibility with the power subsystem. So I'm representing power subsystem just schematically as a battery. There's clearly a little more to it than that, but just you have a battery, then you have a common source impedance going to a common distribution point. So you're going to hang a load off that common distribution point, and it's going to pull some load current, and that basically that forms your conducted emissions. Now, the next session on conducted emissions, we'll get more into the details of what that means, but the first order, that's what it is. You're pulling current, and what you got your intentional DC current draw, and then whatever noise current is riding on top of that. That's your conducted emissions. But you're almost never just hanging one load off the distribution point. You got a lot of stuff to power. So there are many loads that you're hanging off that common distribution point, and all of the loads are going to see the total noise potential at the distribution point. And so that's going to be the total current multiplied by the common source impedance. Again, we'll plunge into more details in the next session when we talk about conducted emissions. And so that's your conducted susceptibility. So one of the key things we'll talk about in the next session is conducted emissions tend to be defined as their individual limits of defined as current emissions on each individual load, but conducted susceptibility is the composite noise potential that will be seen at the distribution point. So, and we'll talk about how we correlate those. It's pretty straightforward, but it's just something you got to pay attention to. But that's for next session. And yeah, CE limits are defined for individual loads, and CS limits are for the composite voltage ripple at the distribution point. So for compatibility with the RF COM subsystem, the raison d'etre of RE102, radiated emissions electric field, is to protect antenna-connected radio receivers. Okay? I'm going to dwell on this because this is a commonly misunderstood point for EMI testing. And the raison d'etre for RS103, for radiated susceptibility to electric fields, is to protect equipment from intentional antenna-connected radio transmitters. Note the apple and the orange. All right, these are not meant to be directly compared against each other. It happens all the time, and wrong. When you compare the RE102, specifically electric field, okay, when you compare RE102 and RS103 limits, and there's so much margin between them, that is incorrect. It's square pegs and round holes. It's a complete misunderstanding of what these tests are all about. Okay, a properly defined RE limit is about protecting the radio antenna connected radio receivers, and so that's your criteria. Do you have the potential to interfere with a radio receiver in that frequency range, right? What the RS limit is in that frequency range is beside the point. It means nothing. Just like for testing radiated susceptibility, are you susceptible to intentionally transmitted levels in that frequency range where you are likely to have a transmitter operating on the platform or at the launch site? Okay, they are completely distinct. So again, verbatim, chapter and verse right out of the mill standard. I'm not making this up. There is no implied relationship between RE102 and RS103. That's basically all the stuff I just said. But it's also right in the mill standard. It may be desirable to tailor the frequency coverage of the limit to include only frequency bands where antenna connected receivers are present. Again, you heard me say that, but I'm not making it up. It's right out of the mill standard recommending that you do that. Now, this is generally above 200 megahertz for Goddard platforms. If you do have a receiver or transmitter operating below 200 megahertz, then by all means you should test there. But if not, we generally start our radiated testing above 200 megahertz. That doesn't mean we don't care what's happening below 200 megahertz. We've just got another way, and what I think is a better way to do it, which is coming up. So the requirements are applicable from 10 kilohertz to 18 gigahertz, this is RE102 specifically, from emissions from the EUT and associated cables. That's a very important phrase there, which is why I highlighted it. The cables are part of the EUT. EUT being equipment under test. That's, again, nomenclature, right? So talking a little bit more about that, when you're doing component or subsystem level or instrument level EMI testing, this shows the general EMI setup diagram per GEVS. It's tailored for mil standard 461G. It basically replaces these LISNs with a capacitor network. Actually, I'm getting ahead of myself. We'll be talking about that here presently. But this is very similar to the diagram in the mil standard, and it just defines a specific configuration for interconnecting cables. So the interconnecting cables are part of the equipment under test because common mode energy in the EUT can couple to cables, most likely will, and the cables in the frequency range where they're a significant fraction of a wavelength, generally like tens of megahertz to hundreds of megahertz, they're going to be your most efficient radiator, right? So the common mode energy can and will couple to those cables, which can and will radiate. And then in the other direction, radiated energy can couple to those cables, which can then carry that common mode energy into the EUT. So a properly designed, quote, box level test with flight representative cables, as they're required to be, and representative loads exercises the cables as much as the box. So to my mind, there is no such thing as a box only level EMI test. We still will call it, box level or component level. But if you shortchange the box or subsystem level test, it only invites additional risk at higher levels of integration, thereby completely defeating the purpose of the test. So let's not do that. So when an EUT meets RE and RS requirements on a military platform, there's generally a low risk of crosstalk because those limits are generally much more stringent, or much lower than they correspond to common mode current levels on cables, culprit cables that are too low to pose significant risk of crosstalk. So outside of radio bands, the default limit may be relaxed. And so this is precisely the reason that RE102 exceedances have historically been the largest sources of waivers on many Goddard platforms. So if you think about, I don't have an example here, but when we get into RE102, the specific session on that, we'll talk about that in more detail. But the way I think about it is, for the mil standard, it's a military standard, right? It was intended for military platforms, or more precisely, or at least one of the target audiences would be contractors who want to provide items for use on military platforms. So a transponder or whatever widget you want to call it, let's just go with a transponder. If I'm contractor A and I'm building transponders, I'm not going to earn my living by building one of these things. I want to build a bunch, and I want to put them on a bunch of different platforms. So the mil standard with a general RE102 limit is basically going to be, if you want to fly on any military platform, well, you're going to have to meet this limit across this whole frequency range. So, okay, you design and build your transponder and test it and verify that, okay, you don't have any emissions that go above the limit over this wide frequency range. Then you know that you can sell this transponder to whatever customer is willing to buy it from you and integrate it onto their platform. That's not how we do things at Goddard, or really within NASA, at least not to that degree. We generally are building onesie twosies. Sometimes, like MMS, I guess we had as many as 16 copies of a given box. We had 4 spacecraft and four copies of a given box on each spacecraft. So we're kind of in that middle zone there. But talking more about like onesie twosies, how most of our missions go, we know what our frequency ranges are for specific radio receivers. We define, those notches that make our RE102 limits look so ugly, but those are the very raison d'etre of the limit. Outside the receiver notches, the limit is rather arbitrary. Your radio receivers are by design the most sensitive device, the most sensitive victim on any platform, because that's what they're designed to do. They're designed to be very frequent, very sensitive in those frequency ranges where they're intended to operate. But outside of those frequency ranges, the limit is certainly much less stringent. It's I hate to say arbitrary, but it's many orders of magnitude less stringent. So this is precisely why Rodney Dangerfield has become our patron saint, because where the limit in a receiver notch is non-negotiable, but outside that it's kind of arbitrary, and we grant waivers for emissions that are tens of dB above the limit because the limit is unnecessarily stringent. But it's important to understand that distinction. So so I didn't include Rodney Dangerfield on this chart like I have on previous presentations, because I don't want him to be our patron saint anymore. So I love Rodney. He makes me laugh, but anyway. A brief aside, I caught a little clip of Rodney not too long ago, a few months ago, and I'd forgotten this one. This is my new favorite Rodney quip. He was on Johnny Carson on the Tonight Show, and Johnny Carson was gasping for air the whole time, and he goes, "Yeah, Johnny, last week I had to disband my fan club. The guy died." Anyway, I love that one. So most Goddard platforms do not use antenna-connected receivers that operate below 200 megahertz. So following this guideline, we only apply RE102 above 200 megahertz. Again, if your platform has a receiver operating below 200 megahertz, you should test there. But the default is that we don't do that. I'll talk about the significance of the 200 megahertz here in just a moment. But so crosstalk is the dominant concern below 200 megahertz. And I love this quote from the late great Henry Ott. He passed away a few years ago. But conducted emissions limits are really radiated emissions limits in disguise. I'll hear, people making a distinction between them. Well, it's a conducted problem, not a radiated problem. And no, they're the same thing, or they're interrelated. So looking at the RE102 test method here, we have specific antenna types in each frequency range. And one thing that's a non-negotiable is that if you're saying you're doing RE102 per the mill standard, then that means the antenna is placed 1 meter from the setup boundary. So I'll have more about this in the RE102 session, but the antennas are calibrated at that distance for a reason. And just a quick overview is, if you've got an antenna that's this big, I mean, it's not necessarily to scale, but it's approximately to scale. You have an antenna that's this big, this far away from a test article. Are you in the far field? Exactly, probably not. So the measurement, when it's calibrated at a distance of 1 meter from the test article, it's taking into account that you're in the near field. It's not, a constant power density over that wavefront and so forth. When you're in the far field, it's a lot more forgiving where you can place the antenna. Okay. But if you're making what is clearly a near field measurement, the distance from the EUT has to be controlled, and it's that 1 meter distance. Okay. So again, more on that in another session, but that 1 meter distance is very significant, that I'll pick up on the next chart. But then the other thing here I'm going to point out is there is an antenna configuration break at 200 megahertz. So that's basically why I select 200 megahertz as that magic frequency, because it's just a natural break point here, that if we're not testing below 200 megahertz, we don't need to use the biconical and the rod antennas, which have problems of their own, which we'll talk about in those sessions. But just 200 megahertz, just because of this makes 200 megahertz just a good frequency break to say we're going to do radiated testing above that frequency, and we're going to do evaluations of crosstalk below that. So looking at RERS versus crosstalk, so the dominant concern below 200 megahertz is cable to cable crosstalk. You know, your culprit box, as we talked about, is gonna couple common mode currents onto. Everything okay? Okay. Everybody still there? Can you hear me?
Yes.
Okay, good.
Yeah,
I heard some
hear you.
beeping here, like a computer was dying, but it was somebody else's. Or intentionally being powered down or something.
It was intentional.
Okay, it's an intentional emitter.
Yes.
So,
No,
so
it's not emitting it.
So you'll have your culprit box will couple common mode current onto a cable connected to it, producing radiated energy, and that radiated energy can couple common mode current onto a nearby victim, which couples into the victim box. Right, that's general nature of crosstalk. So RE102 and RS103 do not effectively address. One reason is, as I just cited, RE102 specifies a 1 meter measurement distance. So without doing any rigorous calculations or analysis, do you think a 1 meter separation distance poses a significant concern about crosstalk? No, probably not. So we're generally concerned for crosstalk. We're most concerned about cables that are much closer together than that, like 1 or 2 centimeters. And any attempts to correlate a measured field at 1 meter to an expected field at a few centimeters is non-trivial and carries a very large uncertainty, right? The near field is very chaotic, as it were. The far field is when things are much better behaved and you have the 1/r relationship for electric field and so forth. And that's why we love the far field, but that's not where we are here. You're very much in the near field. And so if you make a measurement with an antenna at 1 meter and then try to use your 1/r cubed relationship or whatever it is you're using to say, well, it's going to be this at 2 centimeters, it does not work that way. It's fraught with peril and it carries a very large uncertainty, and just that's not the way to do it. So it is more efficiently addressed with direct measurements of common mode currents on cables. We directly measure the common mode conducted emissions on potential culprit cables, and then we evaluate the common mode conducted susceptibility. Oh, I got another typo there. Fix that right.
On your picture, I got a quick question for you.
Yeah.
You say crosstalk is most significant for cable separations of a few centimeters, but you showed 2 different boxes there. Is this more prevalent as wires in the same harness, or are we talking like wire to wire or cable harness to cable harness? Sometimes we have wires from 2 boxes that actually get formed into the same cable harness. So is it all of the above, or is this crosstalk more of one situation over another?
Could everyone hear the question?
Yeah, we did.
Okay, all right. Well, certainly crosstalk can be a concern between conductors in the same bundle and the same cable. That should be addressed with like just the design of that cable, right? If you got a particularly sensitive line, you need that should be individually shielded, or shielded twisted pair, what have you. But what we're addressing here with system level testing are individual cable bundles. So I'm just representing it by a single line here, but that's a cable bundle. That could be a space wire cable with 4 individually shielded twisted pairs in it, or something more complicated. It could be a power cable, what have you. But it's an entire bundle that we're concerned about for system level testing. I mean, certainly crosstalk is a concern between conductors in a given cable bundle, but that should be addressed by the designers of that equipment. Design the cable accordingly, right? If you didn't, you're going to find out just in your own system level, subsystem level functional testing. Actually, this is a good. I'm gonna go ahead. This is be a good time to turn on the camera for just a moment. Can everyone see the camera? Everyone's
Yes.
Yes.
all right. All right, it's not going full screen for me, but that's okay. Oh, there we are. All right. Because I have a sample current probe here. One of the concerns that I get is, oh, you're going to break into our cables or what have you, we have to disconnect, break flake mates, and that's not at all the case, right? These current probes, which we'll talk about when we get into making these measurements, these are generally clamp-on current probe. Everyone see that?
Yes.
Okay. These are clamp-on current probes. You don't have to disturb any of your connections, any of your plate connection. So it opens up, clamped around your cable, you clasp it shut, and there you go. And when you're done, you unclamp it, remove it, no problem, right? As long as you've got, you got room to get it. If it's a group of cables all tied together with tie wraps, okay, well, maybe you need to clip a few tie wraps. But if you're trying to troubleshoot a problem, clipping a few tie wraps to get a current probe in there to see which is your, culprit cable may be a worthwhile thing to do. But just for doing this testing on, even on the bench, or when you bring it in here for a full up EMI test, this is one of the most efficient and I think one of the most valuable tests we can do. It's very easy to do. You clamp the current probe around it. You obviously it has to be connected up to the EMI receiver and so forth, but you get a very direct measure of what is happening on that cable, as opposed to a radiated emissions measurement, which tells you something that the antenna is pointed to is making noise. So current probes are your friend. This is an F33-2, I believe. Yeah, this is one of my workhorse current probes. I use it all the time, and we'll talk about that in another session of, different nuances of different current probes. But anyway, this common mode conducted emissions and susceptibility measurements are a really invaluable tool, and they're pretty straightforward to perform. So going back to sharing the charts, how are we doing on time? Okay, it's 10 o'clock. We're all right. Okay, are we seeing the charts again?
Yes.
Oh, great. All right, let's. Okay, we're right in here. Okay, that's where we were. Yeah, I think we finished this chart, so we'll move on. All right, so test facility and procedure requirements. Updates in Mill Standard 461G. Fast 48 transform machines, FFT receivers, really became much more readily available kind of in the time between 461F and G. So they're really excellent machines. We have one, we actually have two here at Goddard. We have one in the room next door. And they make emissions testing just go essentially blindingly fast, much faster than they have before, using a frequency swept technique. But you need to set them up properly to get reliable results. Something that you can correlate with the standard frequency swept machines, and so they provide guidance for doing that. So that's something that you probably want to know about. Doesn't mean you have to use an FFT machine, but it certainly can make your life a lot easier, if you have one and you know how to set it up properly. Another thing is calibration of measuring equipment. So your primary measurement devices, so spectrum analyzers, receivers, oscilloscopes, multimeters, things like that, those are still required to be sent out to be calibrated to trace using a calibration program traceable to NIST. But passive devices like measurement antennas, current probes, LISNs require no further formal calibration unless the device is repaired. Like these devices really don't change over time unless you drop them or damage them in some way. And current probes are actually really straightforward to calibrate yourself. And I'll talk about that when we get to conducted emissions. If you have a decent cal fixture, you can calibrate the current probe yourself. You know, if you have a network analyzer or a spectrum analyzer that is calibrated, you can do a spot check of your current probes yourself. You don't have to send those out for calibration every whatever year, 2 years, whatever it is.
Yeah, whatever duration we make up, but yeah.
Okay.
So the longer the
Yes.
duration, the more at risk you are of,
Yeah.
if there's an out of tolerance, you then have to go back through that many more years of test reports to verify that
Right.
it's still good. So you want to keep it
But-
between a year or two.
But you know, with all of that, then the measurement system integrity check, which you know you should perform before every test, you know, is sufficient to determine the acceptability of passive devices. That's when you're putting a known signal in. We'll talk about that here. I have a chart on that a little bit later. But you put a known signal into the measurement system, verify that what you're getting out is is the expected value, and it's pretty generous, plus or minus 3 dB. That's the world we live in, right? For EMI, we're in a plus or minus 3 dB world where RF, you know, depending, I've worked RF problems where they're counting hundreds of a dB. So it's a little different way of thinking about things. But with all of that, it actually makes your life a lot easier, right? You don't have to send every single one of these devices out for cal every however long. These are the advantages to using the latest version of a document. This is another public service announcement about that. If you say we're under contract for Mill Standard 461E or D or C or whichever version you like, you're missing stuff like this. Okay. And this is there to help make your life easier. And so if you're deliberately ignoring this, you're not helping yourself. So, okay, test facility and procedure requirements defined in Mill Standard 461G. Section 4.3 apply with the modifications to the following requirements. So we'll talk about these one at a time. I'll also highlight a couple things that GEVS does not tailor in the Mill Standard, but that I think are still worth mentioning. So the ambient electromagnetic level during testing. So some of this I'm just going to read verbatim. During testing, the ambient electromagnetic level measured with the EUT de-energized and all auxiliary equipment turned on shall be at least 6 dB below the allowable specified limits when the tests are performed in a shielded enclosure. So when you hear us say the 6 dB number, that's where that comes from. The ambient level, which is more than just the noise floor of your measurement system. That's part of it, but the overall ambient level that you're capable of measuring before you even turn your EUT on needs to be 6 dB below the limit. So that ensures that you're getting an accurate reading, right? And you do this before you turn the EUT on. If you see all kinds of garbage from the EUT that's 10 dB above the limit, then you shut the EUT off and you see no change in that. You see, 10 dB above the limit, that's clearly all coming from the background in your test environment. Well, you may have spun your wheels on what's the matter with my box before you've actually diagnosed what's going on in your test environment. So yes, sir.
Would be worth mentioning why 6 dB is a thing. Why that 6 dB margin is there.
Andy is asking why the 6 dB is there. I know
why it's,
what's that?
I know why it's there. I'm just saying it might
Yeah,
be
yeah.
for the audience.
And not surprisingly, I have gory details in another presentation on test and measurement, which I'm happy to give at some point. But the noise floor, the background, right? But it's in this context, it's kind of they're basically doing the same thing. Whether it's noise floor or whether it's just background levels, they'll add to the signal level that you're trying to measure. Okay, so let's just say that the background level is right at the limit. So forget about 6 dB for just a moment. If the background level is right at your limit and your measured level the level from your equipment is right at that same level, then you've got two signals. I mean, the noise is just a signal that you don't want, right? But you've got two signals that are, at the same frequency, at the same amplitude. If they are correlated, if they're, synchronized signals, they will add directly. And so the resulting signal will be a factor of 2 higher, or 6 dB, right, in voltage or current. But if they're uncorrelated, which if one is just RF background or noise, then they will be by definition uncorrelated. Then they'll add in an RSS manner, and so the total signal that you'll get will be 3 dB higher. Everybody with me? Just square root of 2, right? You take square root of 1 plus 1, that's the square root of 2. And then when you take 20 log of the square root of 2, that's 3 dB. And so if your noise floor is right at the limit, you could have something that's meeting the limit, like just barely, but your measurement is going to be 3 dB higher, and it's going to give you an indication of that you've exceeded the limit when you really didn't. So when your noise floor or your background level is at least 6 dB below the limit, if you do that same math, which I walk through in another presentation, but if you have noise that's 6 dB below the level and your measured level your real level is right at the limit, then they'll combine to give you something that's 1 dB above the limit. So it's still going to affect your measured level a little bit, but just ideally you want that noise floor and the RF background to be as low as possible, right? But we gotta, saying that it's got to be 30 dB below the limit is not very realistic. So I think it's basically a compromise that if you're at least 6 dB below the limit, that minimizes how much it's going to pollute a signal that's just barely meeting the limit. Okay. That makes sense? Does that answer your question?
Yeah.
Okay. All right. So, so the next, where I'm going to go from here is, because this places an emphasis on minimizing that ambient level. Well, this is not specifically in the mill standard. That verbiage on the previous page is right from the mill standard, but what we add in GEVS are some methods for getting there, right? So in GEVS, in the section list shown there, don't do this. Don't just run your cables from your EGSC through a hole in the chamber wall and connect it to your EUT. Because when you do that, any of the common mode currents on that cable, this is a cable bundle, kind of representing probably a whole bunch of cable bundles, kind of all of the cables from your EGSC going into the chamber. Any common mode currents are going to generate fields, right? Currents generate fields. That's what they do. And if you just run them through a hole in the wall, those currents will come right into the chamber and bring those fields with them. That's going to corrupt your ambient environment and you may not meet that 6 dB requirement that we just talked about. And you're going to compromise your ability to actually meet the limit and measure what's really coming out of your EUT. And you can chase your tail trying to fix a non-problem, right? It happens all the time where we have an apparent exceedance, and then if we trace it to noisy EGSC, like, okay, we could have just averted this problem if we had set things up properly and minimized the contributions from our EGSC. So this is one of the important ways in which we can do that. We terminate cable shields right at the penetration plate. And this is the reason why we tell you to do that. That the current common mode currents, at least ideally, theoretically, will stop at the chamber, and you help them along as much as possible if you provide a nice low impedance path back to the source, because currents will go back to the source. They must. Nature says so. Kirchhoff was just the messenger. Nature says the currents must go back to the source. And if you provide a low impedance path for those currents to get back to the source, that's the path that they will want to take. And it stops them at the wall, and they will not go into the chamber and affect your ambient measurement. A couple of suggested ways to do that. The preferred method is just put a connector break. All right, so you have your feed through plate at the wall. There, lost my cursor. There it is again. So you have the feed through plate at the wall, and that's conductive. Otherwise, it's doing you no good. And you terminate the shield's 360-degree coverage and terminate it to the back shell on both sides. Right, this is the preferred method. There's an alternate method with a stuffing tube, and you would want to remove the jacket from that section of cable, stuff the tube with stainless steel or copper wool, so that you get a good conductive connection of those shields. It's effectively doing the same thing, just providing a conductive connection of those shields to the wall. I have never worked a program when anybody has done this. I've talked to some people who have, but given a choice between what's that? Okay. I didn't support those tests.
It wasn't on purpose.
Okay. But I think generally, like if you're planning in advance, I think most people would rather just build their cables with a connector break than muck with them, once they're here to remove the insulative layer. But the thing is, again, with proper planning, you're probably going to you need to build test cables to support thermal vac, right? This is not going to get you through thermal vac, not very effectively, right? You're almost certainly going to have to build a set of cables that has a connector break to get you through the thermal vac chamber wall. So just build them properly to support all of your environmental tests.
I think this echoes the statement you said earlier about projects arriving or being here 6 months early in advance to talk about testing.
Yeah.
It's a good time for you to say, you're gonna do TVAC, right? So, bam, blah,
Mm-hmm.
the rest of that.
Yeah. So again, proper planning, you can do these things properly, right? So, all right, enough said there. So we're actually doing pretty well here. I think we're getting.
John?
Yes. Oh, hi, John. What's up?
Hi, just a comment about the TVAC cables. They typically tend to be built a lot better than the flight cables. And
yeah,
I guess you'll go into not having cables better than flight for testing.
I didn't mention that explicitly, but yeah, I mean, well, we'll talk about cables here presently. I think that's actually one of the next points, but yeah.
Thanks.
Yeah. Okay. So the mill standard, I got another typo there. Great. Mill standard 4614. All right. Yeah, that's right. It's a new standard. That's when you take mill standard 461 and 464 and just shuffle them like a deck of cards. That was sarcasm for anybody watching the recorded version of this, 20 years from now. Anyway, so all right, mill standard section 435 says the ET shall be installed on a ground plane that simulates the actual installation. If the actual installation is unknown or multiple installations are expected, then a metallic ground plane shall be used. And I'll turn on the camera in just a second to show you our ground plane. So the ground plane shall have surface resistance no greater than 0.1 milliohms per square. The DC resistance between metallic ground planes and the shield enclosure shall be 2.5 milliohms or less. Now, I think I'll go through this next discussion, then I'll show you our ground plane. Okay, so and then one last point on this chart: the metallic ground planes shall be electrically bonded to the floor or wall of the basic shielded room and structure at least once every meter. Metallic bond straps shall be solid and maintain a 5-to-1 ratio or less in length to width. I didn't specifically point this out, but that's a class R bond for I believe NASA standard 4003. So I said ohms per square. Well, so ohms per square what? I get that comment, like when you specify this in a test procedure or something. Well, it's ohms per square what? Per square meter, per square centimeter, per whatever, per square inch? Well, it's per square, as it says. So, and here's what that means. So if you just take some stuff, some material, and one of its inherent properties is resistivity. We designate by rho. So let's take a square of it, and so it'll have some length, some width, and some thickness. Okay. For a square, of course, the length and the width are going to be equal. So the resistance across that square in the direction that I've shown here, we'll say we want to determine that resistance of that square in that direction. Okay. So the cross-sectional area, the way we're defining it here is this width by the times the thickness. Okay. That's our cross-sectional area of this. So the resistance of that square is going to be the resistivity times the length over A. And that's just the textbook relationship between resistance and resistivity, right? Just rho L over A. We'll come back to that. But if we take our square of stuff and then we put another, the same size square of stuff next to it, and they're conductive,
I lost sound. I can't hear.
Yeah,
I
me
lost
too.
sound too,
Same here.
Likewise.
and video looks frozen.
Yeah, I think they dropped off. Hopefully they figure it out. Email might work. I don't know. They probably don't know. I would try to text somebody, but I know for a fact that cell phones don't work very well in that room.
Yeah, I sent
Oh,
an email.
you sent an email?
I did.
Yeah, I'm trying to think what's the, I don't think,
Looks like Yan has gotten robbed though.
oh, okay. I was going to try to text the optical cow guys, but the guy I have the text for doesn't work downstairs anymore. Anyway.
John just texted me that their whole network went down and he's trying to restore it right now.
Thank you.
Yeah, it's funny. The on-site network is less reliable than my home network. Yeah, I got another meeting at 10:30, so I'm gonna jump out. I see some people I haven't seen in a long time. So good to see some of you. Talk to you later.
Take care. Hello, we're back. Can you hear me?
Yes.
All right.
Yes.
The entire NASA network just went down for that period of time, so I couldn't even message you. Doug had texted me. I hope word got to somebody. Oh, I'm glad you all stuck around, but yeah, I couldn't message, I couldn't email or just even message here because the network just went out. But here we are, it's back. So let's pick up more or less where we left off. I was going to go into power source impedance and Lizens. Let's do that. We got about half an hour, so I think we're doing okay for time here. So let's do what we can. Okay, well, thanks for see if I need to restart the recording. I think I do. Oh, well, no, I don't want to stop. Okay, it's still recording. So I may need to do some editing. I will do some editing. I don't think anybody wants to like have that 15-minute pause in there. But okay, let me share. Okay, thanks for your patience and thanks for sticking around or coming back. So, continued with folks in the room here, so I'll just start this bit over again. So, let me actually I'll jump to this for context. So we talked before about common source impedance from your power source to a common distribution point. So that's what this discussion is about, is like what is this common source impedance? And like most things, it depends on your application, on your platform. So let's talk about that. So the general harness impedance model, and we use this as our starting point because you have some conductive connection from your power source, whether it's a battery or whatever it is, to a distribution point. There has to be some conductive connection somehow, whether it's wires or printed circuit board traces or whatever. So that impedance will consist of conductor resistance, some conductor to conductor inductance, and then at high frequencies, you'll get the characteristic impedance of the transmission line formed between those conductors. And this is more, the left diagram is more of the physical representation where those parameters are shared, between the conductors. But we can just simplify that by combining everything to the top leg, to the positive leg, as shown here. And if we just look at that impedance mathematically, we see we have Z naught in parallel with R plus J omega L. And we multiply that out. If we divide top and bottom by Z naught, we get this mess. Well, we can make a simplification here that your lead resistance is generally pretty small. It should be small, right? If you're trying to carry many amps of current, you don't want to dissipate a lot of heat in there. So you're talking milliohms, maybe tens of milliohms, and your Z naught is going to be tens or hundreds of ohms. So generally, we can neglect the R over Z naught term. That's going to be very small. So then we can simplify it some to this expression. And if we graph that, well, what do we get from this? Well, I always find it helpful to break it down into frequency ranges where you can simplify it, right? So if when omega is very small, you can effectively zero it out, you're left with R. So it's just the lead resistance is what you have, that plateau down at the low frequencies. The mid-range of frequencies, it's going to be dominated by J omega L. And at high frequencies, it's going to be dominated by Z naught. So this is a typical, pretty typical impedance curve that you might see specified in a spacecraft source impedance spec or what have you. And and you just see that at high frequencies, the Z naught is going to shunt out the R and the L, right? So you can kind of see at low frequencies, R dominates, then in the mid range, the inductive reactance, and then at high frequencies, Z naught. So this is where LISNs come in. And there are two different types of LISNs. And so the one definition of a LISN is a line impedance simulation network, where the schematic looks pretty much like what I just drew, and it simulates a line-to-line impedance of the power source and the wiring to the distribution point, or conductive connections to the distribution point. And it's generally a self-contained unit. I've got some examples I'll show here once we get through this. And then a line impedance simulation, stabilization network is intended to provide a stable line to chassis impedance of the power source and the wiring to the distribution point. And the high frequency, in this case 50 ohm shunt impedance, is provided by the input of the measurement receiver. So you generally, these types of LISNs, these stabilization networks, generally have an RF port that you connect a 50 ohm cable to it, which goes to the 50 ohm input of a measurement device. So it gives you, you can measure the noise potential there. We'll talk about a bit more about that in the conducted emissions session, whether you want to measure voltage or current. But this gives you a place to measure that potential, but it also gives you that 50 ohm shunt impedance. Right, you can just do the Thevenin equivalent analysis to see that this 50 ohm impedance at high frequencies, when you can basically short out these capacitors, it's gonna basically give you a diagram that looks like this. They don't even really bother with the low frequency resistance here. It's just the inductance and the high frequency shunt resistance, the 50 ohm resistor there. So it generally comes in pairs. You need a LISN on each of the positive and negative power leads if you're going to use these. So we go back to our power distribution diagram. The LISN represents the common source impedance at the common distribution point. It is not intended to represent the wiring impedance from the distribution point to the individual loads. That's a point that sometimes gets confused. So the LISN, when it's properly used, the LISN should be representing this impedance, not this one. So a couple examples here. Typical building or in large platform power wiring. If you think of a large, like a battleship or aircraft carrier or something, these platforms have wiring like what's in a building. If you got sailors who are going to spend many months at sea, they probably want to bring their radios or laptops with them, or anything that can just plug into regular outlets. So it's basically the same type of distribution that you might find in a building. Well, or even think about your house. If you've done any wiring in your own house, the electrical outlets on a common circuit, in the common area of the building, in a room or even a given group of rooms, they're generally daisy chained together. You run one pair of wires up to the nearest outlet, and then you daisy chain them together. So their common source impedance can be quite large. The wiring to the circuit breaker panel can be quite long. Okay, in your house, maybe it's 10 meters or whatever, but in a large building, it could be hundreds of meters. So that common source impedance can be quite high. But on a spacecraft, we generally run dedicated power wires from each load back to the distribution point, as close to the source or the battery as possible. Right, so that common source impedance is typically much lower. And how much lower? Okay, that depends on the platform. I'm not going to get into analysis here, but just conceptually, you can see that this common source impedance is going to be much lower than what you have in the typical building, where you've got a bunch of outlets ganged together. And I've done a demonstration in a video where I take my wife's hair dryer, because obviously I have no use for one myself, but I plug it into an electrical outlet. It's a GFI outlet that's basically part of the light switch in my bathroom. You can plug something into that outlet directly, so it's clearly shared. It's on a shared circuit. Let me go back to here. So I plug a current heavy device like a hair dryer into this outlet that's on a shared circuit with lights. Well, you turn on the hair dryer, you can see the lights dim, right? Because they're connected to a common circuit with this common source impedance. I'm pulling current through this impedance. It's dropping the available potential that I can get across my light. So it's a pretty straightforward example, but you can see how much more complex things can get in a more complex system. You know, you think you got computer systems or what have you that need to be robust against any of the kind of garbage that other people on those circuits can generate. You know, that's why like your clothes dryer is on its own dedicated circuit. So anyway, know thy platform. Right? If you're going to have a device, a LISN, to represent your common source impedance, you want it to actually make sense for the kind of platform that you have. So this is an example of an ISS LISN. An ISS LISN, because ISS uses a couple different ones. And I have one here. I'll turn on the camera in a second to show you. But this is from that SSP 30238 document I mentioned earlier. This is a line impedance simulation network. You can see this topology here is more in line. Now those series resistances are outside to this combination here, but it doesn't really affect the impedance profile in any significant way. But I'll just point out LISNs are generally defined by the inductance value. So it's a 10 microhenry inductor, but remember there's a pair of them. So if you're going to call this a 10 microhenry inductor or a 10 microhenry LISN, it's really a 20 microhenry LISN because there's two of them in there. Now, MIL standard 461 specifies a default 50 microhenry LISN. And so we see the lower part of the curve is the line inductance. That's your 50 microhenries of inductance. And then the higher frequency portion, that's the 50 ohm I say characteristic impedance of the line. That's what it's meant to represent in your platform configuration. But here it's the 50 ohm termination of your measurement receiver is what that's giving you there. But this is intended. This simulates the worst case power distribution wiring on large military platforms, where power is distributed as a single wire 5 centimeters above structure or chassis. Structure is used as the intentional current return path, which we don't tend to do on spacecraft. And so that configuration, that topology will give you an inductance of about a microhenry per meter running as much as 50 meters to a common distribution point. This is in the MIL standard in the appendix. They go through this to say that's where that 50 microhenries comes from. That was the model they used to say that's kind of the standardized LISN that they want to use. Now, this is not realistic for Goddard platforms. So if anybody is insisting on using this type of LISN on a Goddard platform or any just moderate sized spacecraft, this really doesn't make any sense. So in the appendix of the MIL standard, they mention an alternate 5 microhenry LISN. And that may be more realistic for smaller platforms, but I think it's still overkill for most of what we do. So and I'll go through this and then I'll turn the camera on and show you some of what we have here. So for Goddard platforms, the power source impedance is more accurately simulated by a capacitor network. We have a pair of 10 microfarad feed-through capacitors installed between each power conductor and the ground plane. So those are line to chassis. That's an integral part of the standard setup specified by MIL standard 462. So this is going back to an older version of the MIL standard, but I'm providing engineering justification for why we think that's more suitable for us. They're part of the standard suite of equipment available in any EMI laboratory. So any EMI lab that's been around for any length of time will have these. So that's not new equipment that they need to buy, right? As opposed to like custom LISNs, like if you're using if you want to use some non-standard LISN, that's something that you have to develop and pay for. And so that provides a standard source impedance above about 20 kilohertz. Yeah, right. Custom LISNs are not really easy to, it's hard to find somebody who actually build one for you, as we found out. We bought one for JWST some years ago from Solar, but they don't do custom LISNs anymore. But that's another subject. But then we add this 10,000 microfarad line to line capacitor here. Now this is really only something you can use for DC power buses, right? For like a 60 hertz or 400 hertz power system, this is not, this is gonna shunt out a lot of that energy. That's not gonna work very well. But if for a DC, 30 volt DC power bus, that this will work very well, and it's intended to look like a battery, right? As much like a battery, with readily available equipment as opposed to a real battery there. But it extends that standardized source impedance down to 30 hertz. At 20 hertz, this will look like about an ohm. And the 20 kilohertz is where these look like about an ohm. So above 20 kilohertz, these are the feed throughs are really what are doing the work for you. But at the low end, it's the big honker.
You lose him again?
I believe we did.
Yes.
which I thought paid benefits was is
Oh, the network died again. We're back. Can you hear me?
cable design and test cables for all subsystems for the.
Yeah, we can hear you, John.
Yes.
Okay, sorry about that. The network is clearly quite volatile today, but there we are. All right. Well, I can stick around a little past 11 for anybody who's interested. So, believe we're still recording. So,
Yeah, we also have the
Okay.
Wednesday session too.
yeah.
Yeah, as long as at least one person stays in the meeting, the recording keeps going, John.
Okay. Well, so just a reminder, we'll do the same session on Wednesday. I've set it up so we'll do Mondays and Wednesdays. If we'll play this by ear and we'll do course corrections. If it ends up being cover everything on Monday, I'm happy to shrink it to Mondays only. But there probably are some people who can't make it today. So, but if you're here today, you don't necessarily need to come back Wednesday, except in this case where we've lost the network a couple of times. So. But I'll leave that up to you. Anyway, let's keep cranking here so we can finish this up. Let me go back to I believe I think this died while I was talking about Lisons, because I think that's what I finished up with the folks in the room here. So how far into this did we get? Did you guys hear this about the wiring in a building, the outlets getting together?
Yeah, slide 43 is, I believe, what you made it to.
Okay, great. So yeah, I had the hair dryer example where you run the hair dryer and you see the lights dim. We don't really want that sort of thing on a spacecraft. We don't generally do that. So we generally run dedicated wires from the distribution point to each load. So, and if the distribution point is very near the battery, that common source impedance is generally much lower. Okay, now that's a nice, wonderfully vague term I don't like to use, but hey, this is an overview. I'm not going to go into rigorous calculations, but when you connect very close to a battery, just that source impedance is going to be much lower than what you're going to have with tens or hundreds of meters of wiring out to a distribution point. So just the point is that whatever impedance that you use to represent that common source impedance needs to make sense for your platform. So it's, again, one of my mantras: know thy platform. It's on you to know the platform, know what is best to represent what that platform looks like. So this is an example of an ISS LISN. I have a different ISS LISN here. I'll show you in just a minute. And in the interest of time, I think I'll just kind of crank through this, but this is a line impedance simulation network. You can see the topology here, and this type of topology is a line impedance simulation network. It's a line-to-line impedance, and it's generally defined by the inductance value. So the inductors are 10 microhenries, but remember there are two of them in here, so the total inductance really is 20 microhenries. So if you call this a 10 microhenry inductor, that's not really accurate. And it might be what my brain would default to as well, but it's really a 20 microhenry LISN. And so Mill Standard 461 specifies a 50 microhenry LISN. And so you see the 50 microhenries is what's going to define the impedance at the low end. And then the high end is going to be that 50 ohm termination of your measurement receiver. That basically is going to be that shunt at high frequencies. So you have 50 ohms up here. This simulates the worst case power distribution wiring on military platforms where you have a single wire about 5 centimeters above chassis. Structure is used as the intentional current return path, which we don't do on spacecraft generally. And then so this configuration, wire 5 centimeters above structure, will have an inductance of about 1 microhenry per meter, running as much as 50 meters, or just what they standardized. That's what gives you this 50 microhenry number. That's where that comes from. This is clearly very unrealistic for Goddard platforms. So if somebody comes in here saying that, by gum, we're going to use a 50 microhenry LISN because the mill standard says so, they have not done their homework. Okay, it is not an appropriate thing to do for most Goddard platforms. So the mill standard specifies an alternate 5 microhenry listen in the appendix. So that may be more realistic for smaller platforms, but it's still likely overkill for most spacecraft. And I'll show you the innards of one of these things here in just a minute. And so we'll get through this and then I'll actually show you some of the stuff we're talking about. So for Goddard platforms, the power source impedance is more accurately simulated by a capacitor network. So you have this pair of 10 microfarad feed-through capacitors between each power conductor and the ground plane. They're an integral part of the standard setup specified by Mill Standard 462. So yes, I'm going back to an older version of the standard, but because I think it better suits what we're doing. These capacitors are part of the standard suite of equipment available in any EMI laboratory. They've been used for decades. So any EMI lab that's been around for a while will have these. It's not something they have to buy. And it provides a standard source impedance at frequencies of about 20 kilohertz and above. These look like about an ohm at 20 kilohertz and just go down from there. Then we add this 10,000 mic line-to-line capacitor, and I'll show you all this stuff here in just a minute. This extends that source impedance down to 30 hertz. This looks like an ohm at about 20 hertz. And so 30 hertz is the low end of the frequency range for our conducted tests. So this is great for a DC power bus, which is most of what we deal with, 28 or 30 volts DC. You don't want to use this if you're actually dealing with 60 hertz or 400 hertz power distribution. But for DC, this works really well, and it simulates battery impedance. And this replaces the Lisens in Mill Standard 461 based setups, per GEVS. So this, I think, is a good time to turn on the camera and show you some of these things. Let's see here. Now, can everyone see? Can everyone see the camera? Or see the view the camera is showing you?
Yes.
Yes.
Trying to expand this so it's filling the screen so I can see what I'm showing you. Is James still? James?
I think you can press that. There's a little button on the bottom right corner. The little
Of this?
yeah. Oh, right there.
This one?
Yeah. Should be on.
Not doing it. Hold on. I'm just trying to expand this so that I can see what I'm showing them. But are you seeing the camera like filling your screen?
Yeah, for them it is.
Okay, well, that's good enough
That's
for
that
now.
would always be unless you're sharing the slideshow.
Yeah, let's just.
Yeah, that's
fine. Let's get on the right box. It's all that matters. Okay. Another little kink to be worked for. But
Straight up.
Yeah.
One for a ride.
Okay, so I'm just seeing a teeny little. It's just a small little section of my screen, so I'm not. It's hard for me to see what I'm showing you, but we'll get by with this. Okay, so the first thing I want to show you is that this is a different ISS listen from the one that I showed you in the chart, but the schematic, a good listen, or certainly any custom listen, should show you the schematic on the side, and so that schematic should look pretty familiar, right? That's exactly the model I showed you.
Right click.
Right, and this, can't quite, I think these are 10 micro Henry inductors. So I think this may be similar to one I showed you. But the other thing I want to show you here is, this is a 5 microhenry listen. And so the 50 ohm
don't do anything.
resistance is here's the test port, right? This is where you would hook a cable up to go to your measurement device to measure voltage emissions, which would be one of the main purposes of this thing. And there are a couple of capacitors in here, but the main event is the 5 micro Henry inductor. So keep my hand here so you have a sense of scale. Oh, there we go. What'd you do?
Prioritize video.
Okay.
It got turned
Right.
off for some
So
reason.
can everyone still see this?
Yes, we can.
Okay, so here's my hand. You see how big this thing is? That's 5 microfarad. No, micro Henrys. Yes. Henrys is the unit of inductance. Right, so this is a 5 micro Henry inductor. Does this look like something you get by accident? You get 5 microhenries of stray inductance, the parasitic inductance. No, you have to mean it. You have to do this on purpose. And I didn't open up a 50 microhenry Lizen, but you get the idea. 50 microhenry Lizen is going to be even bigger than this. So this is a lot of inductance. Like microhenries of inductance is this is what you have to do to get that. Stray inductance is on the order of like maybe tens of nanohenries, maybe hundreds of nanohenries, you know, in more extreme cases. But to get 5 microhenries, this is what you need. And this is not what we're doing with most of our power buses. So even this 5 microhenry Lizen is kind of overkill. Okay, I hope I made the point. So coming over here to this capacitor network, we're gonna get very familiar with this whole setup in upcoming sessions. But one of the purposes of any of these, whether it's a Lizen or the capacitor network, it's basically the same thing you're doing to a degree with decoupling capacitors on your ICs on a printed circuit board. It's decoupling you from the power source, that it's pulling the immediate current it needs from the capacitor, not from the power source. This is the bench lab power supply I'm using for these demonstrations. It's just this old cruddy Tektronix. It's not cruddy. It's good. It's a workhorse. It's a good workhorse. It's just, it's not as pretty as more recent models, but it's a good workhorse power supply. But you don't want to be tied to any particular source impedance or characteristics of the lab supply you're using. So one of the functions that any of these things do will decouple you from that so that your device under test sees the source impedance provided by the network that you're putting in place, whether it's a Lizen or this. But here are your pair of 10 microfarad feed-through capacitors that it literally is a feed-through. You go in one side and out the other, and then it's lined to chassis. So the case of the capacitor is tied to this L bracket, which is then tied to the ground plane. So you have your two 10 microfarad capacitors, and so the negative lead goes through one of these two. And then we have the 10,000 microfarad line to line. So it's why we call it a capacitor network, but it's just 3 capacitors. It's quite simple conceptually. Now, when you're hanging 10,000 mics off of the power source, some power supplies may scream in pain when they're trying to charge this thing up to get it to 30 volts. This one doesn't. This workhorse supply does fine, but some supplies may go into current limit and may shut down. And so to accommodate that, so we had that happen with some testing when we started using this thing. Was Rick Jones, who's recently retired. He built this little interface box. It's just got a couple resistors and switches in it. So it puts 100 ohms in series with the 10,000 mics while it's charging up. So you get a gentle charge up if your power supply needs it. And then once it reaches, switch it in place. So the 100 ohms is in place when you're charging it up. Then once it's charged up and stabilized, you shunt out the 100 ohms so that now you don't have that 100 ohms in series anymore. So then you have the whole capacitor network in place to basically look like a battery as much as, it's practical. And by the way, as I said, these 10,000 mics are readily, any EMI lab will already have these. This lab, you guys have what, about 4 pairs of these? Not more. Yeah, they have enough of these to support, multiple power feeds on some items under test.
I think we can support up to 5 power services at once.
So 5, okay. And then this, if anybody says, well, we don't have that, well, DigiKey, yeah, it's not flight, all right, I mean, you want it to be reliable for lab testing, but it's not flight. These are readily available for maybe $50. I bought 3 or 4 of these things on DigiKey or some equivalent, maybe 100. About $100. So, okay, let's not exaggerate with 50, but okay, for about $100 and you get it in a few days. So for stuff you already have and $100 as opposed to a custom Lizen, which I think the one that I bought for JWST was about $10,000. So
Yeah.
you tell me which is a more efficient way to go. So, all right, that's enough of this. Let's appreciate everyone hanging around. Appreciate your patience for the network outages. So let's oh, I think, are we down to 3 people online?
One of it's me.
Okay.
Oh, there's 26.
Yeah.
It's just a different view.
Oh, okay. Yeah, I'm only seeing.
Switch
All right.
the view on you, John, so the camera.
That's all right. Well,
James fixed it so it actually worked.
all right. Well, anyway, thanks for everyone who's still there. So, editing this is going to be real interesting. So,
Might be losing you again.
what's that? What was that?
Your audio is breaking up. We might be losing you.
Oh, can you hear me now? Is it okay?
Yes.
Okay. I was moving around a little bit. So, okay, I'm back sitting and back to the charts. So, all right. So, went through all this. Okay, this is what John Lishtick was asking about earlier. So cable assembly shall simulate actual installation and usage. Basically, I mean, the rest of this is just emphasizing that point, that when you show up to do an EMI test, the cables are part of what you are testing. It's always ideal and wonderful if you can bring the actual flight cables in to test the equipment under test, but that almost never happens. I'm not sure I can actually even remember a single time when it did. It's just, part of the deal that you build one set of cables for test and then a dedicated set of cables for flight that you minimize handling with, and you get installed on the spacecraft. So that's just part of the deal, but it means that those cables need to be sufficiently flight representative to provide a meaningful test. And if you can get the flight lengths exactly what you're going to be using in flight, great. But that's also something that doesn't always happen. You might be building your test cables before you know the flight lengths. So you just got to take your best estimate there. But the main point, which really is what's emphasized by those second 2 bullets, the second and third bullets, is the cross section, right? That if you were to take a cross section of your flight cables, that's what your test cables should look like. Any twisting, any internal shielding, and really in particular, your shielding termination technique. Whatever you're doing for the flight cables should be what you're doing in the test cables. And a question when we were going through this, when the network, just here in the room, when the network was down, you don't want, and actually this was John's question earlier, you don't want your test cables to be better than the flight cables because they can mask a problem that could bite you later when you integrate onto the spacecraft. That's the worst type of result, I think. Well, okay, there are a lot of things that are tied for the worst, but here in this case, I will say that's the worst result, is a false pass. When you're masking a problem with your unit level test that you don't see until you integrate on the spacecraft, that's not a good day, right? When you discover that kind of problem on an integrated platform that you should have discovered with the unit level test, your project manager is not going to be real happy with you. So, don't shortchange the unit level test. You don't want to create a problem that's not there, but you certainly don't want to mask one that you have. That's one of the entire purposes of the test, is if you identify the problem there, then you're in a much better position to fix it before you integrate it to the higher level. So again, I hear this all the time. It's the cables, not my box, therefore not my problem. Absolutely incorrect. You are responsible for emissions that your box induces on all cables connected to it. and susceptibilities in your box due to energy brought in through those cables connected to it. The only unit, box level test that I know of like that is devoid of cables would be something like a cell phone that's not connected to a charger, and that's never something that we're testing here. We're always testing something that has cables connected to it. And you're responsible for showing up to your EMI test with proper test cables. So, which always happens. Anyway, all right, no more snark from the room here. Okay, just some more about cables. This is the basic test setup diagram from the mill standard, and this is the one directly from the mill standard. And just note that where it says Lizens, we use the capacitor network for GEVS. But individual leads shall be grouped into cables in the same manner as in the actual installation. Total interconnecting cable lengths in the setup shall be the same as in the actual platform installation. So again, that's an ideal, but sometimes you just have to take your best guess if you don't know those lengths at the time you're building your test cables. So if it's longer than 10 meters, at least 10 meters shall be included, so on. A couple other things to highlight. So at least the first 2 meters of interconnecting cable associated with enclosure of the UT shall be run parallel to the front boundary of the setup. All right, and then at least the individual cable shall be separated by 2 centimeters, excuse me. The cable closest to the front boundary is 10 centimeters back from the front edge of the ground plane. And all cables shall be supported by 5 centimeters above the ground plane. Now I get questions about, well, if the cables are going to be on the structure, on the platform, can't we just do the test that way? And if you know that that is absolutely what you are going to have without exception, even there, I would say you should start the test with running the 5 centimeters, because I don't believe you, right? If you're going to have to route around corners or something like that, at some point the cables may not realistically be directly on top of the ground plane or on top of structure for their entire run. So when this is part of that credibility thing here, okay? If you share your test results and you didn't do the test this way, and you're sharing this with other people who are cognizant of mill standard 461 based testing, they're going to this will be like a big litmus test. If they see that you didn't follow these setup guidelines, they're gonna start scrutinizing everything you did about this test. Okay, but the more technical argument is that when you have the cables 5 centimeters above the ground plane, you get a more shall we say independent assessment of what are the cables going to emit if they're going to emit something. And if you know that they are actually going to be immediately adjacent to the structure, you can take another data set to say, here's the improvement we get when we do that. But when they're isolated above the structure, like with 5 centimeter spacing, then you get a more what the term is really, but it gives you an assessment of what the cable is going to emit if you have minimal cancellation from the ground plane. And I think it's just in your best interest to know that, because then you don't have to worry so much about, well, we're going to have this place where we're not going to have structure under us for maybe a foot or whatever it is. How much of a problem is that going to be? If you're passing in this configuration, then you will pass basically in whatever you're going to have on the platform. I hope that helps. But talking about a peak detector, so the mill standard, this isn't part of what we've tailored in GEVS. This is all right out of the mill standard, but I just want to point out a peak detector shall be used for all frequency domain emission and susceptibility measurements. Okay, I'm not going to bother reading the rest of that in the interest of time, but this may not affect the measured value of a stable signal. It really shouldn't, but it will certainly affect your measured noise floor and background level. And I'll try to whip through this fairly quickly. the network outages have affected our time, but that's the way it goes. So if you look at thermal noise, just like the noise floor, just turn on your spectrum analyzer. Recommend that you do this in your lab or wherever you have access to a spectrum analyzer or receiver. Just turn it. Don't even connect an input up. You're going to get the thermal noise of the system, and you can look up what the on the data sheet what the specified noise floor is. They will generally be specifying an average or RMS noise value, but you're going to get this spread around the statistical spread around that RMS value. And you'll see that the peak is going to be somewhat higher than the average or RMS value. Right. And there's some numerical predictability to this. It's not completely random. We talk about noise as though it's random, and it's not really. So thermal noise follows a Gaussian or normal probability distribution. And I'm just gonna whip through this. I mean, I'm known as the mathicist, but even I hate probability and statistics. And so this was painful for me to go back and relearn this, but bear with me. But so you have this bell curve, right? So this is kind of the bell curve that we all know and love, or I guess know and hate. But if you take just a sample set, just any set of n values, capital N values, the mean is pretty straightforward, right? You add them up and then you divide by the number of samples. Then you take the sample deviation from the mean, just any given sample, you subtract the mean value from it. That's your deviation. Then you take the square of that deviation. Then the variance is the mean of the deviation squared, right? You take this square here and you take the mean of that. You add those up and divide by the number of samples. That's your variance. So the square root of that is your standard deviation, the sigma number that we know and love, or may know and hate, right? But the number that we hear, standard deviation, sigma, and all that crap, that's what this is. That's where that comes from. So it sounds a bit like root mean square, right? You're taking a square and then a mean and taking the square root. It sounds a bit like RMS, root mean square. So so for thermal noise, that sigma value is the value of our RMS noise. And in a whole nother talk, I relate this to thermal noise of a resistor. So these are carryovers from that chart. So that's as much as I'm going to say about this. But that sigma equals the RMS of the noise is the important point here. So when you go back to this curve here, the area under the curve gives the probability of the currents in a given range. So the integral is not possible in closed form. I tried, and then I borrowed a statistics book from a friend of mine who was a professional mathematician for decades. I borrowed his stat book, and they said, yeah, don't bother trying to do that in closed form. Look at the tables in the back of the book. So there you go. If you're ever inclined to do this in closed form, don't bother. But so for a x minus mu, is that variance? That's your deviation, right? So this deviation of one standard deviation unit, one sigma, is about 68%. 2 standard deviation units is about 95, and 3, 99.7. Now I'm going to go to a log scale because it gets really hard to see, but it's the same curve. So 3.5 sigma is about 99.96%. This was just kind of chosen as, when you get to 99.96%, well, any deviation that's more than 3.5 sigma is what I call not bloody likely, NBL. So we effectively can call, for all practical purposes, we can say that the peak deviation is 3.5 sigma values. And it's not really, and theoretically it's infinite, but that's not very practical. Just you have to wait a very long time before you'd ever get any value that's out here. So we can just say that the peak value is about 3.5 times sigma, which recall that the sigma is defined as the RMS of the distribution. So that RMS of our noise is 1 sigma. It's not actually 0. It's 1 sigma. Okay. And I have another presentation where I go through more of the gory details here, but the point I'm driving at here is that the peak value of that noise is going to be about 3.5 times the RMS value. And when you convert that to dB, well, 20 log of 3.5 is 11 dB. That is what is cited as the crest factor for thermal noise. And you may have heard that term, but that's where that's where it comes from. It's a statistical thing. That's all it is. It's just taking statistics on a bell curve is where this is. I never saw this defined in any textbook or anything like that. It's just fellow EMI engineers who shared this with me. Henry Ott mentions it kind of in his book, but he doesn't really go through the calculation. That's kind of Henry's style. He just gives you the answer, but that's okay. That was Henry. But it just means that the noise floor peak will be about 11 dB higher than the RMS value, which is likely what is going to be specified in your manual for your measurement device. Okay, so going back to our figure here, the peak value of the noise is going to be about 11 dB higher than the RMS value. That's the crest factor. And so if we go to an RMS detector and just take a bunch of averages, we get this curve here, and then just with the marker there at whatever 350 megahertz, it's about minus 83 dBm. And then when we go to positive peak, just a peak detector and max hold, and just let the display integrate for a bit. Lo and behold, we're right around 11 dB higher. We went from minus 83 to a little above minus 72. So, we're within half a dB of that 11 dB number there. I call that close enough for rock and roll or jazz or government work. But the point here is MIL standard 461 requires measurements with a peak detector. So your noise floor will be about 11 dB higher than the specified RMS value in the manual for your measurement device. So if you're looking at low level signals and want to determine what your noise floor is and what's the range of signals that you can actually measure, you need to take this 11 dB number into account. So I think this is a very important thing. That's why I thought it was worth spending a little bit of time on, so that you understand where this 11 dB number comes from. So, and with that, we just got a couple more things here. So for susceptibility testing, MIL standard 461G specifies maximum scan rates and maximum step sizes. Analog scans, I think, are basically how things were done yesteryear. I think we pretty much only do step scans at this point. Well, if we just look at an example to see what these numbers mean, let's just look at, we'll keep the math simple. We'll look at a starting frequency of 1 megahertz. So in that range, the step size is 0.01 F naught. Well, what does that mean? Well, it means that your next frequency is 1.01 times, well, F naught in this case is your 1 megahertz. So the next frequency is 1.01 megahertz. And then your next frequency after that is just 1.01 times that. So just over 1.02 megahertz and so on. That's all that means. It's quite straightforward. So in GEVS, for the first 3 frequency ranges, we keep things the same. But above a gigahertz, we've relaxed the step size to 1% of F naught as opposed to 0.25%. So that's a 4 times relaxation. So using this, experience has shown using this step size, these scans above radiated susceptibility scans above 1 gigahertz can take basically an eternity. So now they only take about 1/4 of an eternity. So again, if you want to use this, nothing is precluding you from doing that. Just be aware it's going to take longer. But for the most part, 1% of F naught is sufficient to really weed out any problems. I don't think there's a real risk of missing anything, and it just makes those tests the more efficient use of test time. A little bit about modulation. The MIL standard specifies this 1 kilohertz pulse modulation, 50% duty cycle. So another bit of terminology for you here is just a straight up continuous wave. A sinusoid is called a continuous wave or CW signal. So you'll hear that term. It's just a CW signal. Well, that's what it means. It's just a straight up sinusoid. And so pulse modulated, I've compressed the scale a little bit here, but it means you're on for 500 microseconds. If it's a 1 kilohertz, 1 kilohertz period with a 50% duty cycle, you're on for 500 microseconds, off for 500 microseconds. Yeah, so implications for detecting and imaging systems. To first order, noise is determined by taking statistics on pixel data. So you take mean and standard deviation of sampled pixel values, generally with respect to some reference frame. You might take, so for a typical pixel period of 10 microseconds, at least in systems that I've worked on, so a sampling rate of 100 kilohertz, any frequency above 50 kilohertz will be undersampled. And that's most of our radiated susceptibility frequency range. So the susceptibility at any given frequency will manifest itself as the total energy integrated over a pixel period. Right? You're going to get multiple cycles of your susceptibility signal over this 10 microsecond period, and just the way you're sampling it, you're just going to get the total integrated energy over that period to give the sampled pixel value. And so at any susceptible frequency, an unmodulated or CW continuous wave signal will produce an approximately equally shifted signal in all pixels. So if you perform statistics on these kinds of frames, they'll show a shifted mean if you're looking closely enough, but the standard deviation will not look much different from a non-RS frame. This is a false pass, which I've said many times is the worst type of result. You get a false sense of security that everything is fine when it's not. And we've had this happen. We had these detector systems look like there's no noise when we know bloody well there should be, like when we had seen it before. And it was when I can't claim credit for this. It was when a fellow engineer named Ike Orlowski, for any of you who know Ike, he went back and looked at the data and said, wait, the mean is shifted. And he said, we didn't modulate the test signal. I bet if we modulate the test signal, we'll see it. Well, lo and behold, we did. So if you apply the modulation, you get this herringbone pattern, and it will, so just visually in the image, you'll see it, and then it'll clearly show up in your statistics. So, in these more homogeneous areas here, that's where the modulation was on the off cycle. So just visually, you can kind of see, well, it doesn't look like there's any susceptibility here. So here's a case where you need the modulation to kind of effectively mix things up a little bit so that it's more obvious that you're going to have a susceptibility. Now it's not going to produce a susceptibility where there isn't one. It just means it's going to be much easier to see if you are susceptible at that frequency. They'll give a counterexample of a pressure transducer. Just any device that basically gives you some kind of steady state DC value as a function of the measured quantity, in this case, pressure. And so the applied susceptibility signal will just ride on top of that DC potential. So if for a modulated signal, you're going to get basically the modulated signal that you're applying will ride on top of that DC potential that you're trying to measure. That may be a little bit weird to try to quantify your susceptibility, but a continuous wave signal might be much easier to actually to see, right? If you're going into a power meter or something like that, or even a scope, because the test that I'm thinking of where this was brought out, we were just looking on a scope, and I think just measuring the RMS value on the scope. Well, whatever it is you're doing, the CW signal may be a lot easier to measure and quantify the susceptibility in this case. So if so, you get to tailor the test method and specify, well, we're going to apply a CW signal instead of modulation, because you are making the engineering judgment to be able to make the most use of your test time and say, here is the best way to actually evaluate whether we have a problem or not. So again, know thy equipment under test. One of the cool things about this line of work is you get to learn a little bit about pretty much everything that goes on the platform. You might not be able to design it yourself. I mean, I can't. I'm not going to design you a star tracker, but I'll learn enough about how the star tracker works to say, okay, how do we make best use of our test time to determine that we're testing it right? Like, how does this thing work so that we know how we're testing it? Mention the measurement system integrity check. It's basically when you apply a known test signal into the signal chain. And what's not really shown here is your data recording device then feeds into, in our case, a software package where you're applying, then for this, in this example, an antenna factor. If it's a conducted test, it's a current probe factor. But you're applying a known signal in, and then you're going through your entire chain, through your software and everything else that backs out the measured potential to the quantity of interest, electric field or current or whatever it is, and that you're doing it correctly. This provides the confidence in your measurements, and don't skip this due to schedule pressure. Okay, hold your ground, because this is an important thing to include in your test report, that you did this and that you can stand by the measurements that you took. If you didn't do this, if there are questionable measurements later on, where you're trying to convince systems engineers or project managers that you've got to put a halt on things to fix a serious problem, and if you didn't do this, it's gonna be a big chink in your credibility. Yeah. So don't put pressure on the lab to skip this step.
Oh, we're gonna do it. Bill's the bill.
Yeah. All right. I'm sure we're near the finish line here. So just general setup per mil standard 461G figure 2. And then in GEVS, we modify that to replace the listens with a capacitor network, and just emphasize we terminate shields to back the shells at the feed through panel. Okay. This is coming back to our painter quiz. Remember this? So who painted this, and how old was the person when it was done? Any guesses? Some of you, I think, already know this, since you've seen this before. What's that? No, it's not Van Gogh. Not a bad guess. No. Anybody online? I like that guess, but no, it wasn't.
Yeah, we're still online. But no, I
Okay.
don't know who that is. I can't
But
remember.
anybody, any guesses?
How about Albrecht Dürer, and that's the Cranach guy.
No? All right. Well, I'll give you the answer. Well, it's called Man with Beret. So that's a very, clever, witty title, right? Pablo Picasso at the age of 14. So why do you suppose I told you this? Why is this relevant to any of the stuff I've been talking about for the last 2 hours? Because if you can paint like Rembrandt when you're 14 bloody years old, that's when you can get creative with the rules. When you know the rules inside and out, that's when you can get creative with them. I mean, if Picasso could paint like Rembrandt when he was 14, that helped me understand everything he did for the rest of his life. It's like, okay, I'm bored with that. I'm going to do something else, because I can do that. And I'm not going to paint Rembrandt-like portraits for the rest of my life. I'm going to do my own thing. But it's only when you show that you know the rules inside and out that that's more meaningful. So don't go all Picasso with EMI tests unless you know exactly what you're doing, is really the point. I don't really recommend going Picasso with EMI tests in general, but the point is, know the rules inside and out before you start getting creative with them. All right, I'll quote chapter and verse of the mill standard for you. Then I'll tell you, okay, here's why here's where we're going to deviate from it and why. And it's not just, well, we don't feel like doing it that way. It's like, I know full well that the mill standard says this, but it also says tailor as needed to your application when it's backed by, proper engineering judgment and assessment. So in summary, read GEVS and mill standard 461, and we'll get on to detailed test methods in upcoming sessions. Here I'll open it up for questions or commentary. Anybody have any questions?
John, you made a comment that your project customers are more often now than they used to come into you 6 months in advance with questions and asking for your guidance. Did you do anything in particular to establish that relationship so that they initiate that conversation earlier?
Yeah, I mean, I was the project EMC engineer on a lot of those, so I made sure it happened. I mean, I have Goddard's a weird place in a lot of ways. I probably shouldn't go in that direction. But in terms of EMI, we do things a little different from I think most other NASA centers where like I'm actually not in the same organization as the EMI lab. So I'm, supposedly the chief EMC engineer for the center, but I'm in a different organization, different functional organization than the EMI lab. They're in the environmental test group, part of thermal vac and vibe and everything else. But I'm in the electrical systems division on the project support side. So I've been the project EMI engineer, and on those projects, there's no other way to do it. I come talk to these guys and well, then after a number of test campaigns, then I know, okay, here are the things that we need to do to prepare for an EMI test. But I'm also kind of, on a consulting basis with most projects on center, and I give them a polite little nudge that when they start making any noise about EMI testing, I say, hey, give Rob Hool and Andy over in the EMI lab a call and start that dialogue, right? And I'm very happy to see that they don't, when they call Rob and Andy directly and don't have to go through me and I'm not a middleman anymore, like that's great. That's the way it should be. They should be able to talk to these guys directly, because the more I'm a middleman, the more I slow things down, and that doesn't help anybody. But just, yeah, if you don't know your EMI lab guys, get to know them. I think I can't speak for EMI lab guys everywhere, but if you come to them with an honest request to learn a bit more about what they do and to be the most effective when you bring something there to test, I'm pretty confident that they will be very happy to spend some time with you and talk to you. So,
Thanks. Appreciate the answer.
who was that speaking?
Hi, John. It's Mike Garrett from NASA Glenn.
Oh, hey. Okay.
Yeah, we don't have that type of structure. So I'm sort of on the test facilities side, and we don't have integrated EMC engineers. It's sort of the electrical engineers in general have that responsibility. And I do, the ones that do come to the lab, after they finish that set of tests, I tell them next time, please come back earlier when you're, even your PDR. So that's how we're doing it. But yeah, we're not embedded in the projects.
Mike Carlocker retired then.
What's that? Okay.
He was the EMI guy over there.
Yeah. Anybody else have any questions? Comments, things to make better. The network loss wasn't something I had direct control over. They did. But I appreciate everyone sticking around through the count them two times the network went down.
That's just the one we know.
James
Hey,
said
John.
that's just the one we know about. Oh yeah, hey Sean, what's up?
Yeah. So, not sure if it's worth it, but just thought about it when you went by. You talked about the Lizens and what's good enough for NASA. Not sure you said why we ended up there, or can you say a little bit more about good enough for NASA and or why we ended up with the capacitor network instead of the other previous design?
Well, I did to some degree, but I'll just reemphasize some of the points there. I mean the 50 microhenry Lisen, the default in the mill standard, the 50 microhenry Lisen is clearly way overkill for any typical spacecraft. I mean as I mentioned, the 50 microhenries is based on wire above structure, power distribution on those types of platforms, or to wire 5 centimeters from structure running as much as 50 meters. And that's just not what we do. When we tend to run a dedicated return lead with our power leads, so the inductance per unit length is much smaller, and 50 meters is just, that's much larger than any of our typical spacecraft. I mean, 10 meters might be kind of on the outside for I mean, even a large spacecraft. So so okay, in that case, you might be getting to something on the order of a couple of microhenries, but just the so the 50 microhenries is just way outlandish for anything we typically do, and even the 5 microhenries is a bit, I think, is a bit extreme. And so what, where we landed with the capacitor network is that if you have, man, go back to these charts here. If you, on a typical spacecraft where we're running, we run dedicated wires from the distribution point all the way out to a load, individually, that is, so that shared common source impedance is really just whatever wiring you have from the distribution point back to the power source. And in some on some spacecraft, that distribution point is actually on a printed circuit board in some equivalent of a power distribution unit, or whatever the power system calls it, a PDU or what have you. And so those leads will come back to connectors on that box, and that distribution point is however it's implemented, a really big trace or a plane on that card with a lot of capacitance on it, with thousands of microfarads of capacitance at that distribution point, between the point and the signal reference. So on those types of platforms, just a significant capacitance, or even ideally, I mean, a battery is really what's dominating your source impedance. Or the common source impedance is really whatever conductors you have getting you from the battery, whatever the source is, to the distribution point. So those tend to be more capacitive dominated buses than inductive. And when you do put a capacitor network there, like we do with these tests, to represent a battery, if you think of a conducted emissions measurement, basically that low impedance that the capacitors are providing you, that's representing a battery, will be able to source whatever current the EUT wants to pull. In particular, noise current. So you don't have any significant source impedance there that's going to limit that current. You'll get a worst case assessment of whatever those current emissions are going to be, whatever the EUT is going to pull, that source impedance will be able to provide it. And when we get to the hands-on workshop portion for differential mode conducted emissions, I'm going to show you how the Lisen impedance will limit that current, and again provide you an optimistic assessment of what the emissions are, which again is not desirable. So any significant impedance there, 5 microhenries or especially 50 microhenries, is going to limit the current emissions and give you an optimistic result. Does that help?
That's great. And for your Lisen design, how early do you need to make decisions on your Lisen design in your program?
Well, if you go with the capacitor network, there's nothing to design. I mean, I maintain that gives you kind of the worst case, so that whatever the just thinking of conducted emissions in particular, that gives you the worst case in current emissions, that once you know your spacecraft source impedance, then you can apply the measured current emissions to whatever that impedance is to give you the worst case voltage emissions if you need to do that. But if you just baseline this capacitor network from the get-go, there's really nothing to design and nothing to analyze. It kind of gives you the worst case. And you know, at least that's my best answer there.
No, I think I was thinking not just Goddard, which is, you know, definitely equipment we have, but you know, here and there, maybe more and more, you know, there are different houses that are doing the test, and not sure if they have those listens as a standard item.
Every
and
commercial
if we can
EMI
share.
lab is gonna have those 10 microfarad feed throughs, so that's not gonna be any added cost to a particular project. Trying to build a simulation network, you're gonna pretty much be doing that yourself at your lab. All the vendors in the United States and probably outside the United States that I'm aware of that actually makes listens will not make you a simulation network, because like John mentioned, for JWST, you're going to spend at least $10,000 or more just to get one listen made, where you can buy all the components for a cap network and build it yourself for less than $500.
Mm-hmm.
So,
well, I'll point out that on a program that got canceled about 1.5 years ago, and that I understand is trying to be revived, but to remain nameless. But they were specifying a custom listen. They were specifying a simulation network, not a stabilization network. So you needed 2 inductors, 1 on each lead. It was a pair of 2 microhenry inductors. And I had an intern, was one of the projects I gave her, well, 2 years ago, to try to build this thing. And I had never tried to build one either. Of course, I was helping her, but what we learned is how hard it is to build a reliable listen that works up into the higher frequencies.
I'm just a listen doctor.
Right. You know,
Hard.
I wish I brought that. I think it's in my lab, but maybe one of the next sessions I'll bring it up here. But you know, well, here, let me I'll turn the camera on. I can at least show you.
So it may be worth explicitly stating too that the mill standard wasn't necessarily designed around a battery distribution power system.
Yeah.
Which is why you have such a huge difference between spacecraft application versus mill standard.
Yeah. But can you see the camera on? Can you see the listen again?
Should be.
Anybody still there? Can you see the listen? I got the camera, the external camera on.
Yeah, we can see it.
Okay. So this is just a large gauge wire. I don't know exactly what gauge it is, but it's, you know, it's meant to carry tens of amps of current. In fact, I think, yeah, 50 amps. So, but look at these additional, these successive windings of this thing. We talk about the hidden schematic, right? So this is, we're calling this an inductor. We're calling this a 5 microhenry inductor. But what's the hidden schematic? What do we have between these windings? Anybody?
Insulator.
Capacitance.
Capacitance. Who was that? Who gets the gold star? Was that Sean?
No, Chris Bloom from ULA.
Oh. Okay, well, you get the gold star. Yeah, you're going to have capacitance between these windings. That's a really hard thing to control. Okay, I'm actually impressed that they got this thing to work. I mean, the wire, this may be specific wire the wire itself is probably much smaller than this insulation. So if it's spacing between the successive windings is how you control the capacitance. And what Annabelle was the intern that I had trying to build this listen. What we learned is that's a really hard thing to control if you've never done it before, if you don't really know what you're doing. And it took many iterations of rewinding the thing. I mean, you got to try to get the value you want. You need 2 microhenries, and there's a rather complicated equation for for actually, you know, like the practical limitations of doing it. I mean, the theoretical, you know, equation for number of windings for a given inductance is pretty straightforward, but then taking all that other stuff into account, it makes it more complicated. But we never really quite got there. Like the impedance will look pretty good up to maybe 10 or 20 megahertz. But, you know, we're trying to specify this thing out to 50 or maybe even 100 megahertz. It gets wonky really fast, like above about 10 or 20 megahertz. It gets really hard to control those parasitics. And it's really hard to get a controlled impedance out to those higher frequencies. So when people are specifying these custom LISNs that they won't provide you, they'll just say, well, you need to build one. Like, so have you actually done this before? Was kind of my question, and I never really got an answer to that question. Like, you know, if you built these things and you have a reliable house that you go to who builds these things for you, we'd love to get one for our testing.
I'd love to get a couple high power ones from the Mag site too, so put me in touch with your contact, if you have somebody. Just saying that whoever else out there,
Yeah,
let me
right.
know.
But the point is building these. I mean, this is a standard LISN, you know, a 5 microhenry, you know, the alternate LISN, but this is a fairly standard LISN. And I'm not sure if this looks like a solar product. I don't see. Oh, Stoddard. I'm sorry. Yes. Goddard. Yeah. Okay. So Stoddard right there. But if you have a house that's still building these things, so much the better. But it's very non-trivial to build one of these things because that you got a lot of things to consider. I mean, 50 amperes says right there. That's a lot of current, so you need a big wire to handle that. And then you need, you know, to know what size of PVC tube you need and all this sort of thing. It's non-trivial to build one of these things yourself. Somebody have a question?
Go into a DC application or 60 hertz.
Yes, all that. Does somebody have a question or comment out there? Okay. Are there any more questions? All right. Well, thank you all for hanging out this long and especially with the two network losses. But we'll do this again Wednesday. I hope we don't lose the network. If you want to, certainly welcome to come back to fill in any of the gaps that you might have missed. But yeah, spread the word. The more the merrier. So
Good job, John.
thank you.
Thank you.
What's that?
Thank you for doing this.
Certainly. We'll
Cheers.
see you more. All right, bye-bye.